Algebra 2, target 22. I can write exponential growth and decay functions for appropriate situations. First off, our focus is exponential growth. What is exponential growth? There's a couple of situations that are really nicely modeled by exponential growth. One you should be familiar with if you've ever been in a science class is the growth of bacteria. Take a look at a bacteria. If you start with one cell, eventually the cell will multiply, split, and become two cells. So 1 will become 2. Continue it, each of those cells will grow and eventually will multiply. Each cell there will split into 2 more. All right? And then those 4 cells, those will grow and mature, and they will split each of those into 2 cells. And it will continue in this method, doubling every time, every day, as long as it's allowed to continue. This is called exponential growth because you're repeatedly taking your previous amount times 2. All right? Here's another example. This is an example of a calling tree. You need to get a lot of information out quickly. What do you use? Use a calling tree. You start by calling 3 people. The number of people that have been informed is now tripled. Each of those people then calls 3 more people, and the number of people that knows the information is now tripled again. Right? That's the power of exponential growth. What you have before determines who knows next. You start with one person, you triple it, not a lot of people know. But if you triple, like if 20 people know and it gets tripled, a lot more people know. So exponential growth is growth based on what's happened before. It's signified by repeatedly multiplying the amount that you have from level to level. Right, here's another example of exponential growth. You can see these numbers approximately triple, and you can see how quickly the growth is occurring here on the bottom. The ratio from level to level is pretty similar, but each level gets larger and larger, quicker and quicker, because it's exponential growth. Classic example of exponential growth is the population of the world. It took the world 1,804 years, I'm sure from the year 0 AD or BCE or CE. Took the world 1,804 years to reach 1 billion. To get the next billion, it only took 123 years. And it only took 33 years to get the 3rd billion. It's getting quicker and quicker because the growth is dependent on how many you have, because it's exponential. All right, so here's the model we're talking about. When a real life quantity increases by a fixed percentage each year, we can be modeled with the equation y equals a times 1 plus r to the t. All right, another way you could say it is a times b to the t. The 1 plus r, that's your growth factor. R is your percent increase. Okay, so if you have something that's increasing by 100%, we would put 1 in for R. So it would be y equals a times 1 plus 1 to the t, or we'd have y equals a times 2 to the t. So if something increases by 100%, you can see our growth factor is 2 because it's doubling. So your percent will go in for r, and that'll give you your growth factor. Right, so in the exponential growth model, y equals 527 times 1.39 to the x. Identify the initial amount, the growth factor, and the percent increase. All right, our percent increase, remember we like to write it as y equals a times 1 plus r to the x. Our percent increase is this r value here. Well, if you take a look, what number has been added to 1? Well, r is 0.39, so that means our percent increase is 39%. So then our growth factor, it's a 1.39 growth factor, meaning your previous amount is being multiplied by 1.39. And to find your initial quantity, you always plug 0 into the equation. I'll give you your initial quantity. If you throw 0 in for an exponent, you get 1. And so our initial quantity is 527, which coincidentally, or not coincidentally actually, the initial quantity is A. So we start with 527. We grow at a rate of 39% for a growth factor of 1.39. Pause this, try this, and hit play then. In 96, there were 2,573 computer viruses and other computer security incidents. During the next 7 years, the number of incidents increased by 92% each year. Right, an exponential growth model, given the number of incidents T years after 96, about how many incidents were there in 2003. So our equation, y equals a times 1 plus r to the x. A is our initial amount, so that would be 2573. R is our percent increase, so if we're increasing by 92%, R is 0.92, so 1 plus R is 1.92 to the x. So here is our equation. About how many incidences were there in 2003? Well, x, or they said t, it's just a variable, use whatever you want. I'll throw t in there so I try not to confuse you. T is years after 96. 2003 is 7 years after 96, so we'll do y equals 2573 times 1.92 to the 7th. All right, so we'll plug that in. 2573 times 1.92 to the 7th. There were approximately 274,000 incidences. 247,000, sorry. And then we'll graph it. Take a look at our y equals. We'll enter our equation. 2573 times 1.92 to the x. Take a look at our window. We should probably set our window. Let's go negative 10 to 10 for min to max. If you think about the min, think about the y value, the lowest number of incidences you can have is 0. The highest number of incidences we had so far was 257,000. We're talking our x window goes for 3 more years. So let's make this like 2 million for our max. Scale, I'll make 500,000. And when we graph it, we can see that exponential shape taking place, where it's slow growth at first because your amount of growth is based on how many you have. If you don't have a lot, you can't grow a lot. But the more you get, the more you can grow from. All right, so take a look at here. In 1992, 1,219 month parakeets were observed. For the next 11 years, about 12 more parakeets were observed each year. Write equation. All right, our equation, y equals a times 1 plus r to the x. A is our initial amount, so that's 1219. R is our percent increase, which is 12, which is 0.12 as a decimal. So we have 1.12 to the x. All right, try the next one. Pause and go over it. You purchase an antique table for $450. The value increases by 6%. Our equation here, initial value is $450. Increased by 6%, which is 0.06. So 1.06 to the x. That should be the equation. You want to find what it's worth in 10 years, plug 10 into that equation. Okay. Pause and try it. In 2000, average price of a football ticket was $42,828. Your next 4 years, price increased by 6% per year. Write a model. All right, if it's a percent increase, it's exponential. The rate of increase is 6%. So that'd be 1.06. The initial amount is $48.28. And then x represents a variable. We'll put in any number between 1 and 4 to find the price after 2000. One final application is money. Money grows in a bank exponentially. It's called interest. They'll compound it. The compound equation is a little different than what your last equation was because they compound it a certain number of times. They don't wait for the end of the year to compound it. So we take our rate, divide by how many times we compound it. So if you're getting like 12% interest, you don't get 12% at the end, you get 1% each month. And then it's compounded however many times per year. So take a look at this final example here. You deposit $4,000. That pays 2.9% annual interest. Find your balance after 1 year if you're compounded with the given frequency. All right, so if you're compounded quarterly, that means you compound 4 times per year. So our equation, initial amount is 4,000. 1 plus our percentage is 2.92, so 0.0292. Break it into 4 pieces. Compounded 4 times in 1 year. We'll calculate that out. And you'll have $4,118 at the end of the year. Trying the next one. Instead of 4, you go 365 because it's daily. And you got 4,118, 51 cents instead of 9 cents. So that's exponential growth. Tomorrow we'll look at what happens when you go the other way, going down, and that's exponential decay.